All right, I think we are ready to go here. So, good morning, everyone. Thank you for joining this webinar. We're going to be talking all about parking structures, and specifically, we are going to be talking about the Kiwi Newton Kiwi CarPark System. So, first off, if you have any comments and questions throughout the webinar, please feel free to use the Q&A in the chat function there. Put them in at any time. I've got Janine on my end. She's going to be grabbing all the questions, all the comments, and then trying to consolidate them, combine any questions that might be the same. And then at the end, we're going to have a question period. I'll go through the ones that have come through, and any others that start popping up in that Q&A section, we will get to all of those. This is going to be a bit of a longer webinar today. I've booked it for about 2 hours just because I wanted to put everything that I could think of into this webinar, all the frequently asked questions that we keep getting, everything you really need to know about parking structures in general, and then everything you need to know about using the Kiwi CarPark system to design and to build your parking structures. So let's get ourselves started here. So first things first, I just want to give a really quick introduction to Kiwi Newton. So Kiwi Newton is a North American construction company that was founded back in 1994. We've really built a reputation for delivering innovative and high quality building solutions. Originally focused on traditional construction as a general contractor, Kiwi Newton has expanded its capabilities by incorporating a lot of modular and prefabricated methods into its operations as part of a vertical integration strategy. So by integrating design, engineering, and manufacturing, we can offer a streamlined approach that reduces costs, shortens timelines, and enhances sustainability. So our in-house production facilities for steel fabrication and precast concrete allow us really to maintain a full control over quality and supply chains. And through this long history of project experience, Kiwi Newton has become more than just a general contractor. Kiwi has really evolved into these 6 main areas. So design build, general contracting, Kiwi modular solutions, net zero buildings, automation and prefabrication, and design and construction services. The Kiwi Newton vision is to be a single source for planning, design, fabrication, construction, and even maintenance for buildings. As a vertically integrated design builder, we will design the building, manufacture the modular components, construct the building, and maintain the building. We are also able to assist in planning and different stages of feasibility. So our mission is to provide high quality, affordable, and sustainable construction at scale. And our strategy builds on these 3 principles. So first, we need to think like an automotive company. Next, we need to leverage process standardization with design flexibility. And then lastly, invest in automation and robotics for prefabrication of the modular components. So since 1994, Kiwi has built over 1.5 million square feet of residential. We've installed over 30 megawatts of solar through our Kiwi Solar division. We've built over 5.1 million square feet of industrial, 1.5 million square feet of commercial, 1 million of institutional, and over 3.1 million square feet of parking structures. That's all to say that we understand construction and we understand parking structures. So here's a list of the parking structures we've completed here in North America to date. And we have a few more that we'll be adding to this list probably in a few months, or at least within this year. Now, having completed so many parking structure projects, we've collected really the top things that can really derail a project, all the way from design decisions to cost impacts. And these are things you really should know before starting the process. So this is a posted article on our website. And so if you're thinking about building a parking structure, I highly recommend at least skimming through this list. You can access it here. You can scan the QR code. It's a great resource if you're thinking or you know you're going to be planning a parking structure. But one of the fundamental issues we see is that parking structures are approached as if they are just simplified buildings, but they behave a lot more like exposed infrastructure. And when we confuse these two categories, we underestimate what the building needs to endure. Quite frankly, parking structures have more in common with bridges than they do normal occupancy buildings. I think we get tricked because a parking structure, it's a box type building. The form feels very similar to an office building or a commercial building. But infrastructure, like bridges, dams, sewers, they don't look like buildings, right? So they're easy to fit into that infrastructure category. But in infrastructure construction, it's really where short-term thinking leads to problems. So thinking about the construction materials and the construction methods as trivial, that leads to big problems. Parking structures are exposed to weather. They carry repetitive vehicle loading, they deal with the icing salts and chlorides, they require efficient traffic movement, they need strong drainage strategies. So durability matters a lot more than fancy interiors, and life cycle maintenance is a major issue. And unlike normal buildings, they can suffer from things like freeze-thaw spalling, salt and chloride infiltration, carbonation, water migration through joints, hidden reinforcement corrosion, rust stains, deck coating failures. And when a structure like this deteriorates, they look unsafe, they feel neglected, they communicate decay, and they erode institutional trust. And this reflects really poorly on whatever business or institution, airport, hospital, casino, whatever it is. It will reflect poorly on that business. And of course, deterioration can lead to much larger impacts. And this is the kind of things that we are looking to avoid when we purposely design and build parking structures. So, in many ways, parking structures are simple. If planned correctly, you don't need HVAC systems, building envelope, insulation, all that stuff. But that means that the structural elements are exposed. So I'm not going to go through this whole comparison list. This might be better for, a rewatch of this webinar at some point. But the key idea here is that occupancy buildings are designed to keep the weather out, where parking structures must perform when that outside inevitably gets brought in. So, normal buildings are primarily real estate assets. Infrastructure projects are primarily functional service assets. Real estate is often judged by usability and revenue, where infrastructure is often judged by reliability, durability, and life cycle value. So, a normal building may have heavy use too, but much of it is protected indoor space, where infrastructure is often more exposed and more abused. So therefore, parking structures shouldn't be built like your generic occupancy office buildings. They need their own construction method. That's why we adapted a prefabricated building structure construction method that was originally developed in Europe, and we made it applicable for North American standards and North American environments. So what we need is a construction method that prioritizes concrete staying in compression to eliminate cracking. We focus on concrete stresses and design the structural system to reduce top surface tension. If we can reduce tension, we can reduce cracks, and that can reduce a lot of the issues. Also, if concrete stays in compression, it actually can have some kind of self-healing properties. Now, second, we use a concrete mix that is designed for exposed infrastructure. We use UHPC, which stands for Ultra High Performance Concrete. This is much denser and much stronger than normal concrete. This reduces porosity for freeze-thaw pumping and carbonation issues. Third, we use hot-dipped galvanized steel sections for columns and beams and reduce the amount of reinforced concrete. So by doing so, we keep the important steel in observable areas, reducing any hidden rebar that could have issues that, we frankly can't see. So we use hot-dip galvanizing for all of the exposed steel. We prioritize inspectability of the structure, And we prioritize true ductile behavior, even in failure. And in engineering terms, I don't mean failure as in collapse. What I mean is failure is when the structural elements stop behaving like they should. The system, quote unquote, fails when we get inelastic deformation. So, like a goal in structural engineering is that if a building is going to fail, we don't want it to collapse. We want noticeable changes so that people can get out and that we can do something about that building before it collapses. And then lastly, we aim to remove the weak links, or maybe better put, remove the need for the weak links altogether. So if you find a weak link in an approach that is important yet is going to be prone to failure, we want to determine why it's important and then find a better solution than whatever that weak link item is. I mean, this is really the core concept of any sort of continuous improvement type of thinking. So we remove failure paths where possible. And we have seen that membranes fail. Therefore, we want to design a system that does not depend on membranes. No membranes, no problem. So by engineering a specific construction method for a specific type of building, we can reduce construction costs, we can reduce maintenance costs by up to 90%, we can create unique buildings with nearly limitless facade options, we can increase driver and pedestrian safety, we can streamline construction schedule, we can reduce CO2 impacts, and construct buildings that have over 100-year lifespan. Now, I will make a quick note here that the Kiwi CarPark system is designed for permanent parking structures. However, we do have a variant of the system that can be demounted. Now, this isn't temporary, but this would be something you'd likely want in place for maybe 10 years or so before demounting it and moving it to another spot on the same property. Or at least within the same municipality, so that the parking dimensions are the same. Use cases for something like this might be for like airports, hospitals, universities, colleges that have many parking lots and are not really sure what the long-term development plan is. So they might put up a demountable structure on one of their parking lots with that ability to move it to a different lot on the same campus in the future if they want to develop that initial parking lot. So I want to make this distinction that this is not some sort of temporary parking system that you can lease for a couple months or you can put up for a weekend. The reality is that temporary parking structures, they do exist in Europe, but it's very challenging to do this in North America. Several have tried, and I believe they have all failed. I don't want to go too deep into this here, but we do have a whole article written on this if you're interested. All right. So what is the Kiwi CarPark system? Well, let's start with the main components of the system. What makes up the core part of the parking structure? First, we have hot-dipped galvanized steel columns. These are erected on the outside of the parking bay, so you don't have these, in any of your drive or parking areas. Then we have hot-dipped galvanized steel beams. These span between the two columns. Then we have our ultra-high performance, our UHPC precast panels that sit on top of the steel beams and connect to them. Now again, UHPC, this is not your typical concrete. It's got a very dense matrix, reducing porosity, and it's significantly stronger, almost 3 to 4 times stronger than your typical concrete. Then we have precast concrete stairs. And one of our typical details for our stair towers is that the two outer walls are actually made of ventilated glass. The two interior walls are your precast concrete. It not only looks good, but this is a huge element for user comfort. So like if you look at these images here, particularly at night, this is very comfortable for anyone who's going to be in that stair tower. There's a ton of visibility from the outside looking in. And we also use ventilated glass. So there's actually gaps between the glass panels. And so sound can also transfer out as well. So if you compare this to 4 walls of concrete making a stair tower, that's very uncomfortable, especially if it's late at night, and you're going up the stair tower to get to your car after your shift or something. This is just a really nice way to make users feel a lot more comfortable. Speaking of walls, so we use our precast walls for things like those inside walls of the stair towers, elevator cores, and other necessary walls inside the structure. We manufacture these in our shop, and we can do things like we can put the door frames into the mold before we pour the concrete, so we can lock those door frames nicely into the concrete. We also use conduit that we put into the molds before concrete. Conduits for things like the electrical and for data lines. And that's just a way that we can bring more work into the shop and do the work inside as much as possible. And then lastly, this is a bit of a bonus part of the system. We also have the ability to use precast foundations and retaining walls. So this is a great option for speed and cost. However, it's not appropriate for all projects. I'll say that, sometimes depending on distance and ground conditions, cast in place footings just might be more cost effective. But we look at both of these options for every project, and we just figure out which option is the most cost effective. So those are the main components of the core structure, and this is how we put it together. So we first put up the steel columns, we put up the steel beams, and then we install these temporary jacks on the beam. And what this does is it just creates a camber in the beam, or it actually maintains the camber in the beam because we manufacture the beams with that camber. Then we put the precast on top. We grout the precast to connect to that steel beam. We'll do this for all the levels that we need to. We're going to erect the full height of the building. Then once the precast panels are grouted and the grout is cured, we are going to remove the jacks and we're going to let that beam sort of start to deflect back downwards. And then we're going to end up basically at this final state here, which is what it's going to look like: the steel columns, beams, precast, and the grouting in between. You can see some of the pictures here. Like I mentioned, we erect full height of the building. So we actually have a time lapse of one of our parking structures. So this is for Humber College in Toronto, Ontario, Canada. So before I start this video, I just want to bring your attention over to this area here. You're going to notice we're going to start at the back and we erect the full height of the building, and then we move the crane back a few grid lines and we do the same thing. So let's just start the video here. So you can see we erect that stair tower, and then we erect all of these levels with our crane, and we're just going to start stepping back really nicely. And what's nice about this process is because we stay within the footprint of the building for the majority of the erection, keeps a very nice, compact, and clean site. You'll notice too that this project has a small building off the side. You're going to see it in a second here. This was a 2-story office building that housed security and parking offices. I think there was a bike storage and some coffee shops and retail. There it is here. There was a coffee shop. I think a little bit of retail in that as well. So this is outside of the footprint of the building. So we could actually treat that little officey building as a separate building, which is actually a very important consideration from the building code perspective. And then the project also has solar panels on the east and the south side, as well as the roof. This solar array actually generated way more power than it uses, but the college used it to offset power usage from one of their other buildings, and they're actually they were able to make that other building completely net zero. So one thing you'll notice in the assembly process is that I didn't mention anything about the application of topping. And if you remember from the strategies before, I said we want to limit our membranes or our toppings. So as mentioned, parking structures are harsh environments. We got water, chlorides, freeze thaw, and constant traffic coming into the building. And many conventional solutions manage durability by relying quite heavily on full surface traffic membranes, usually some sort of epoxy. This membrane is something that usually requires stripping and replacing every 5 or 6 years. often requiring that then the structure, or at least part of the structures, have to be put out of service while you do that restripping, or while you do that stripping and redopping. Our approach is different. So when we think of these buildings as infrastructure and we implement those strategies that I mentioned at the beginning of the webinar, we come up with a construction method that reduces reliance on epoxy topping. Now, we don't get rid of it altogether. We only really need that epoxy topping at the joints where two of our UHPC panels come together. So we use that durable UHPC deck plate and a pretty smart design strategy that keeps the driving surface in compression. And so let's go back to this slide for a second. We have our ultra high performance concrete panels that sit on top of our steel beams and connects to them. This is actually a big differentiator to this construction method. Now, not only do the panels connect to the steel beams, but they become a composite section with that steel beam. This means that the UHPC and that steel beam actually work together as one cross section. So for the engineers in the audience, you likely see the importance of this, because if those two things work together, when the beam bends, the UHPC takes compression while the steel beam takes all of the tension. This is great because concrete is really good in compression, but less so in tension. And concrete typically cracks in tension, and we don't want cracks. That's kind of the whole part of this, is we do not want cracks in the concrete. Therefore, as part of these intentional design choices, we get to use prefabrication, but still create a composite section of steel and concrete. This is beneficial for strength of the overall section. Composite sections are stronger than just steel and concrete sitting on top but not connected. But this is also beneficial for deflection limits and for vibration. But even better, let's add a cherry on top of all of that. With some smart erection processes, we achieve a sort of, I'll call it post-stressing of that concrete, where we use the dead loads to put the concrete into compression from the start. Let me explain it a little bit more. See, the steel beams are fabricated with a camber to them. So camber just means that they're purposely curved so that we curve them upwards. So the middle of the beam is actually higher than the two ends of the beam. Then when we erect them, we use those temporary jacks to basically keep that camber, to keep that curvature. So like I said, the middle of that beam, it's going to be maybe an inch or two higher than the ends of the beam. Then, over here, we place those UHPC plates on top. We grout it all together. We let that grout cure, which now locks that precast deck into that steel beam. Then, and only then, once it's cured, do we release the jacks. So here we start releasing the jacks. And so what happens is the dead load of the panels and the beam itself, that wants to settle. So essentially, it wants to settle to remove that camber in the beam. But since the precast is locked to the beam, as that deflection starts to occur, the precast goes into compression and the beam goes into tension. So effectively, we're post-stressing this composite section, leaving that concrete in a perpetual state of compression, which is a good thing. And we're left with a flat concrete deck. I mean, it's not flat. We do need slopes for drainage, which I might mention a little bit later. But the steel precast composite section ends up essentially flat along the length of the beam. So that shows the stresses really in the longitudinal direction. But let's also quickly look at stresses in the other direction, as the UHPC is really simply supported basically from beam to beam. But first, let's take a look at a typical sort of double T setup. This will show you what we're trying to avoid. So note, this is a cross section of a bay where the car in this example might be driving down the drive aisle. So looking at this cross section, the deck basically behaves like a continuous beam. And the moment diagram would look something like this. So I know this is getting a little bit technical, but it's an important consideration, and you can't really design infrastructure without technical input. So the moment diagram here shows us that we have areas of compression. Compression would be the positive moment, and areas of tension, which is negative or hogging moment. This is shown in red. But if we look at the slab in these two locations, so if we look at this location, we can see that the top of the slab is going to be in compression, and the bottom is going to be in tension. And the neutral axis is going to be up here because we likely have some rebar in the bottom to take some of the tension, while the concrete in the top takes the compression. This type of stress profile, this is good. This is actually what we want, because that top surface of the concrete, this is in compression. But now let's take a look at the stress profile right here over top of one of these T's. So what we end up with is basically a reversal of the stress profile. So the top of the slab is now in tension, and the bottom is in compression. And then the neutral axis is going to be somewhere down here, because now we would have rebar in the top of the slab to take that tension. So we'd have rebar in the top there. So this is a problem, because even with rebar, tension in concrete is going to lead to cracks. And cracks in concrete is not something we want in a parking structure. So like normally in normal construction for an office building, a residential building, institutional building, cracks are okay. The concrete really is meant to crack, and the rebar takes the tension and everything essentially works as it should. But parking structures are different. Cars are going to bring in water and salts into the structure. And if this salty water gets into these cracks, it's going to get to the rebar, and that rebar is going to start to corrode. That is why this type of system requires that topping membrane to basically protect those cracks, to cover it up. Now, let's look at the Kiwi CarPark. So same setup, but now you'll see that the moment diagram only has negative moment, the good kind of moment, because the deck plates are really, they're simply supported from beam to beam, meaning that the tension causing moment can't occur over the top of that beam. And the flexural stresses, if we take a look at that over here, they look pretty similar to what we had up here. Compression in the top, tension in the bottom, neutral axis is somewhere here. But over here, you're going to notice that it's nothing, because there is no flexural stresses occurring here, because that moment is zero. Now, of course, there's still going to be shear stresses, but there's no tension or compression right at this point. So no tension, no cracking, no worries, essentially. And so the result of that, the result of the simply supported, the result of that composite section, the result is this biaxial compression in that UHPC deck plate. This seems simple, but this is a very important aspect of how to make parking structures more durable. And so why do parking structures built this way last even longer, even though they don't need topping? Well, to simplify it, let's look at these three key reasons. One, we use a special ultra high performance mixed design to increase the density and reduce the porosity of chloride infiltration. Second, we're going to use smart engineering details to keep the top of that UHPC in compression, while the galvanized steel is going to take all of our tension. And then lastly, something we haven't even really talked about yet, but we manufacture the UHPC and the steel actually in our controlled facility. We do this partly because you can't really do cast in place UHPC. The concrete sets really, really quickly. And also partly because it would be very difficult to get consistent quality of UHPC deck plates on site. UHPC mixes require a high degree of quality control and very precise measurements of the inputs that go into it. So all of these things need to come together, but they can when you intentionally develop a construction method for a specific use case. This works because we're thinking about parking structures properly. We're thinking about this as a specific use case infrastructure project. Here are just some of the images of our manufacturing shop. So we manufacture the components of the Kiwi CarPark system in our steel and precast manufacturing facility. We utilize things like automation for precision, quality, and risk mitigation. When we design, manufacture, and build our projects, we have the ability to adapt and react really to any of the changes that might happen on a construction project very quickly and very effectively. Now, I have spent a lot of time talking about the durability of the UHPC, but what about the steel? The steel is exposed. Will this not rust and corrode it? Well, this is why all of the exposed steel is hot dipped galvanized. Galvanizing isn't a new process. It's very well understood, and it's understood as a very good way to protect exposed steel. So the chart below, it shows that with roughly 4 mils of zinc coating, which is pretty standard for the sections that we're using in the Kiwi CarPark system. With 4 mils of zinc coating, the time to first maintenance is over 90 years for this red line, which is a suburban environment. So this means that the time to first maintenance, this is not collapse, this is not failure, this is not we need to replace the element. This is just time to first maintenance is 90 years in a suburban environment. Even if we looked at, let's say, industrial or tropic marine, we're still above 70 years. And what that means, that time to first maintenance, this is defined as the point in time which maybe 5% of the steel surface might have some rusting. And so what you do there is you just maintain it. You reapply some galvanizing, you fix those key areas. So, first time to first maintenance, 70, 90 years, means that with some maintenance, this is going far beyond a 100-year lifespan. Okay, so now that we've got some of the technical stuff covered, I want to talk a little bit more about how to plan a parking structure with the Kiwi CarPark system. Now, there are a few key things I'll mention here quickly about planning a parking structure, but I won't go into full detail, but I will remind you that we've got this article which goes into more detail on all of this stuff. But basically, when we're planning a parking structure, we basically want to try to minimize the square footage per parking space. So if you take the entire GFA of your building, divided by the amount of parking spaces in your building, you'll get your square footage per parking space. Typically, we see a good efficient layout is about 300 square feet of parking space. If you're up at about 350, you're still probably okay, but if you're getting to the point where you're 400 square feet per parking space, there's likely a lot of inefficiencies in your layout, and there are different layout things you can do to bring that closer to that 300 to 350 square feet per parking space. Parking structures have ideal dimensions, and we really want to make sure that we're designing within them. I'll talk quite a bit about this in a second. But we also want to really focus on, let's design, build a solid structure, the core elements, and then let's make it look good. Then let's add the facade. Then let's add those extra aesthetic elements. For parking structures, ramping is really important, right? We have to get cars up and down different levels, so we want to make sure that we're designing those as efficiently as possible. We also want to try to stay above ground if we can. Underground parking is quite a bit different than above grade parking structures, and it really is much more expensive to do underground parking. So if we can, let's try to keep the parking structure above grade. We want to also work with one-way slopes. Designing parking structures where the floor slopes in two directions, it starts to add a lot more complexity in the constructability of it. So if we can work with slopes in one direction, we need slopes, whether it's for ramping or for drainage, but we want to try to keep them just in one direction. We also want to keep a consistent structural grid. And lastly here, I'll just say that parking structures do not like quirky shapes. And I'll relate that actually back to the first point. So if we have a weird shape, we've got curves, we've got angles, it's going to be hard to utilize the square footage in that kind of quirky areas. So the square footage per parking space is going to go up because we're going to end up building square footage that doesn't go towards parking. And so it's going to increase your square footage per space. And when it comes to construction projects, I mean, you're basically paying on a square foot basis. So to make it the most cost effective, we want to reduce the amount of space that we have to build. So when I look at kind of starting with just like even a concept for a parking structure, the first things that I want to do is I want to start with my parking space and aisle dimensions. This is going to be defined and decided by the municipality. So you want to go to the zoning bylaw and you want to pull out the dimensions for a parking space length, a parking space width, and your aisle width. So you can see in this image here, you've got your parking space length, the length of a parking space, the parking space width, that's going to be the width, and then the width of your drive aisle. So it does change quite a bit throughout North America, but some of the typical dimensions that we see is it's about 6 meters for the length of a parking space, 6 meters for the drive aisle width, and then you're going to have another 6 meters down here, and then you're going to have about 2.5 to 2.8 meters for parking widths. This varies quite a bit, but what that does is it defines the width of a parking bay. So we want to really design our parking structures, the width of the parking structure building, we want it to be in increments of a parking bay. And this is what I mean by a bay. So the bay is basically parking length, drive aisle parking length, and you can kind of see it here, parking on each side. Why do we want to stick with a parking bay and design in increments of this? Because this is a very efficient way to get your parking. You've got one drive aisle and you're, we'd consider it a doubly loaded drive aisle. You can park on both sides of it. So the bay width, this is essentially just going to be 2 times your parking space length plus your drive aisle. And this is a key dimension that we want. And then the length of the building, this is less critical. Basically, the parking structure length is just going to be in increments of your parking space width. So if it's, let's say, 2.6 meters is a parking space width, the entire length of your building is just going to be in multiples of that. And again, that's just a way to utilize your square footage as best as possible. So let's actually run through a quick example here. I think this is going to be a really good way to show some of the design elements. So this is a parking structure that we've designed before. I've just highlighted the parking lines just to make a little bit easier to see. But let's start with this and kind of go from first principles and work on how we would put this together. So the first thing we're going to sort of think about here is in relation to the components of the Kiwi CarPark system. So we're going to have our steel columns, we're going to have our steel beams. What you're going to see here is the distance between these columns. This is going to be your parking space width. And then the length of that steel beam, this is going to be your parking bay width. And on top of those steel beams, we're going to put our UHPC panels, and we have 2 panels that will sit on the length of a beam. So you can kind of see, here's a good image here. This is our steel beam. It's, on our steel column. So we've got one plate here, and then we're going to have another plate here. You can also sort of see it here. So this is one UHPC panel on the width of the bay. We're going to have another one kind of spanning over here. So here you can kind of imagine the entire floor plan, the entire layout. So we're going to have columns all the way on this kind of grid line across the page here. We're going to have columns across the grid line here and columns down here at the bottom. And then we're going to have these steel beams that are going to be spanning between each of the columns. So once we've put the deck plates on, we're going to have that parking bay width, which is column to column. And then in here, we're going to put the parking spaces. So parking space length, we're going to have that drive aisle in the middle, and then another parking space length. So what you can kind of see here is we've developed one bay of parking, right? So here we actually have, I think it's 38 parking spaces long. So the length of this parking bay is just 38 times this parking space width. that's going to be the length of the building. The width of the bay, like I said before, parking space length, drive aisle width, plus another parking space length, that gives us that entire bay width. So now that we've defined basically this one bay, what we're going to do is we're going to double it, right? We're now going with what I would call a 2-bay parking structure. So we have 2 bays side by side. So the overall building width is essentially just going to be 2 times the width of that parking bay that we kind of defined earlier. And you can kind of see in the background too, I still have that drawing up. So we actually define the grid line in line with all of those beams, with those columns, and essentially where these parking spaces are going to be. So you can see all these different grid lines. That's how we're going to set that. Now, if we look at it like this, it looks like we've kind of got a nice, efficient parking layout, right? But if this is the entire floor plate of our parking structure, we need a way to get from this drive aisle essentially into this drive aisle beside. So what we're going to do is at the ends, we're going to take 3 of these parking spaces on each side. So basically 6 parking spaces here. We're going to remove them. And now this gives us a nice ability to drive from this parking bay around and into this parking bay. And when we remove 3 of those spaces, that gives us the necessary like turning radius and stuff that we need to basically get from, one bay to the other. So now this is looking pretty good. We have a parking structure floor. We have 2 bays side by side. This is quite efficient in terms of how many spaces we get over the entire area of this. And we've just taken out 3 spaces here, 3, so 6 over here and 6 over here, and we can loop ourselves around. But with a parking structure, we're still going to have to add stairs. We need some stair towers because obviously we need to get out of the building. If we have an elevator on the project, we're going to need things like elevators. We also need some extra room on floors for things like maybe electrical rooms, mechanical rooms, or at least a electrical mechanical closet. We might want some storage for maybe some bike parking. So there's something sort of interesting we can do with this layout to get some more space, but not lose any parking spaces. And that's by taking these end parking spaces here and actually rotating them inward. We moved that drive aisle in, basically 2 grid lines in. We're doing it on the same side over here. And now what happens is we end up with these blank spaces here. One thing I will note is we did not lose any parking spaces, and I can prove that to you. So let's just go back. Let's take a look at, let's start at grid line 34, I believe, which is right here. So we have 1, 2, 3, 4, 5. So 5 spaces, 5 spaces. We have 10 spaces. And then 1, 2, 3, 4. So to the right of grid line 34, in this layout, we have 14 parking spaces, right? Now let's go to this layout. Let's again look at grid line 34. So here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So again, to the right of grid line 34, we still have 14 parking spaces, but we've gained these areas in the corners. Now, these areas in the corners, these are going to be perfect for adding our stair towers, for adding elevators, elevator lobbies. It's going to be great for things like mechanical rooms, or even if it's just blank space, we can use this for things like bike storage and everything else. So in this actual floor plan, you can see we have the elevators down here. We have the elevator lobby in front. We have a stair tower over in this corner. We have stair tower here. I believe this is like an electrical closet or something here. And then we end up with just kind of free space in these 2 other corners here. This is great for storage. We might put bike storage or something like that in there. Now, if I bring back the structural elements, the columns and the beams here, you're going to see that we have the columns all in these grid lines and columns on this grid line here. But if we have a drive aisle that looks like this, obviously we can't have columns in this area. So what we're going to do is, if we look here, we're going to remove these 2 columns. And then we're just going to add a beam from this column all the way to this column so that these beams can now sit into that column. So we don't have columns in this area, which of course is necessary if we need to be able to go from one side to the other. So here you can kind of see this is that beam that I was talking about. This is the beam here, and we have a drive aisle so we can actually go from one bay into the other. So just an important sort of note on the structural system of what we're doing to get from one bay to the next. So let's go back to our floor plan here. We have a great floor plan. It's very efficient in the space that we're using. We have all of our parking spaces. We have drive aisles. We can go from one side to the other. We have elevators. We have stair towers. But how do we get from one floor to the next? I don't see any ramps on this floor plan. And this is where a two-bay structure is very nice and it's very, very efficient, meaning it's very cost effective. Because what we can do is we're allowed to park on a slope that is a maximum of 5% grade. So we can actually take one of these bays, or we can take both of these bays, and basically in this area here, we can slope that floor up to 5%, and we can end up with this, basically this helical flow up the building. We can go all the way up, and we're actually going up and down the building just by going from bay to bay. This is obviously exaggerated. We've kind of pulled this out. These, like I said, you would be a maximum about 5%, but this kind of shows you nice and efficiently how we can get these layouts done. And this is great because this is very effective in terms of using our square footage as much as we can for parking. We're not building extra square footage just for ramping. We're actually using the bays themselves to get this ramping. Now, you have to have a long enough structure. So in this example here, we do have a long enough structure because what you could do is say we could go half a level here. So 5%, if we did half a level from this side to this side, and then another half level up this way, that would basically determine the shortest building that you can have. I think it's somewhere usually around the 50-meter length that still allows you to do this kind of two-bay sloping structure layout. But what this looks like in reality, this is actually the structure that I was using here in this floor plan. You can see two bays side by side. And basically this bay here, this one is essentially flat. And I say essentially because we still need some sloping for drainage and stuff. But this bay over here, this is the one that's, roughly 5%. I think it ended up being somewhere more like 4%. I can't remember exactly. But you can see how it's sloped upwards. And so you would just drive up and you would drive around. And if you imagine floor by floor, you're just getting yourself kind of up each level. Here's just a little video. You can kind of see it. Sometimes in a moving context, it's a little bit easier to see. Let me just kind of bring it around. So yeah, here you're starting to see kind of that floor below and how you would just kind of rotate yourself or helically drive yourself up the building. I really like these layouts. This one here. I find this is the most intuitive layout because if you imagine coming in as a user of the parking structure, you drive in and you have to go by every single parking space as you go through the building. So you'll essentially find the nearest open parking space just by driving. And so there's no like unintuitive left turn, right turn, backwards, forwards. It's very intuitive. You go into the building and you just find the next spot as you're driving through the building. So here are some of the typical sort of parameters and dimensions of the Kiwi CarPark system. So the UHPC panel, so the actual precast panel itself, is about 105 millimeters. We can go up to 125 millimeters thick if needed, but for an open air above grade structure, we use 105 millimeters thickness. So it's actually quite a thin panel. That's what the UHPC allows us to do because we've got the strength of that ultra high performance concrete. The width of the panel, that's going to be anywhere from 2.5 meters to maybe 2.85. I mean, I think we could go up to 3 meters if we needed to, but this is going to be based on the width of the parking space. So you're going to find that in your municipal zoning bylaw. They're going to tell you what the minimum dimension of a parking space is going to be. And then we actually make the width of the panel essentially that same width. The length of a panel, I mean, it can be anywhere from 0 meters to, up to about 9.5 meters because we're putting two panels across the width of the bay. A bay is typically going to be around 18 meters long. Again, this is all going to be defined by the municipality and the bylaw of what the dimensions of your parking spaces and drive aisle need to be. But the length of an individual panel is just going to be half the length of the entire bay. The steel beam, so the depth of that beam is typically going to be it's around 600 millimeters. Sometimes with the length increases because of the bay width increases, it might change that steel section, but we're going to be typically about 600 mils deep. The length of that beam, it's just going to be the length of the bay width. So whatever that ends up being. So that means that the overall floor thickness is typically about 700 millimeters. Again, there's variance in here, but the steel beam plus the UHPC that sits on top, it's going to be about 700 millimeters. So if we use a clear height difference, so the clear height would be the top of the floor to the bottom of the steel flange. That clear height is, again, typically set by the municipality. It might be in your zoning bylaw somewhere, but we see the code minimum is usually about 2.1 meters. So we want 2.1 meters clear. However, we can make that height really as high as needed. So if you had, let's say, sprinter vans or larger vehicles that you want to be coming into the structure, we can make this as tall as you want. A lot of times what we see is the ground floor, that's going to have some sort of taller floor to floor or taller clear height, just for the requirements of maybe some larger vehicles coming in. And then we might go to the minimum clear height for the floors above. But if we use the minimum clear height of 2.1 meters, that means, excuse me, that means that the floor to floor height, so the top of the floor to the top of the floor above, is typically about 2.8 meters. Again, we can make that as high as we need, but it's typically going to be somewhere around 2.8 meters. This is nice, and this is actually a smaller floor to floor height compared to cast in place garages or double T's. Those are closer to 3 or 3.1 meters floor to floor. The slight benefit to that is, let's say you have a property and you really want to max out how many cars you can fit on that property. We can fit more floors in a given height compared to another construction method. And the reason that's important is because building code will limit the height of a parking structure building to about 22 meters. So with our system, we can get eight or nine floors within 22 meters, whereas other systems, you are limited to about 7 or 8. So we can get a whole extra floor within a footprint using just a floor-to-floor height that's a little bit less. Now, one thing to mention is that the higher your floor-to-floor, the longer your ramps are going to have to be, because you need a ramp. If it's a sloping floor system, you're limited to 5%. If it's a different kind of a ramp system, it just means the higher your floor-to-floor, the longer your ramps are going to be. And speaking of ramps, this is a great time to talk about them. So there's kind of 3 main ramping systems that I would say we see with parking structures. The first one here is what we call a dedicated ramp. So you have a dedicated ramp off the side of your building that's going to go floor to floor. The next one is going to be that sloping floor system. So this is what I had kind of shown you before. If you have at least 2 bays side by side, you can use the bay itself sloped at a maximum of 5%, and you can use that to get up each level. This image here is showing you 3 bays, and that middle bay is the one that is sloped. The third option is a split level structure. So if we kind of look at a cross section here, what this is 2 bays, again, side by side, but one bay is higher than the other by about half a floor height. And what that does is allows you to get a short ramp into the structure, basically between those 2 bays. I think I've got a layout coming up that might show a little bit better. But by having one bay only half a floor higher, you can kind of go up the bay or up the structure, kind of going side to side, bay to bay. And again, it's a very efficient use of your floor area. The downside, I would say, with a dedicated ramp is you have to build this square footage, and you're not parking on this ramp, right? This is just a ramp to get you up to each additional level. So that's more square footage you have to build without getting parking out of it. And again, the higher floor to floor you have, the longer your ramp needs to be. Something to consider here, just with a dedicated ramp system. So dedicated ramps, typically the maximum slope you can do is about 15%. And so even with a 15% ramping system, your transition areas, I believe, can't go more than 8%. So what we have to do is we have these 2.5 meter long areas where we do half of the slope. So if we're 15% here, we're going to do about 7.5% here. And we just basically transition from 7.5 to the full 15. And then as we're coming down, we transition back to 7.5 and then back to 0. The reason why we need these transitional sloping areas is so that your car doesn't bottom out. If you go straight from 0 to 15, chances are a vehicle, especially a low riding vehicle, is going to bottom out trying to make that curve. So we just use this 2.5 meter length, and we go half of the full grade here. In terms of that dedicated ramp, the width of these usually ends up being somewhere around 18 meters or so. So you've got, 8 meters. You have about 8 meter wide, and then the length of this ramp, this is all going to be determined by your floor to floor. It's going to be determined by the maximum grade percent that you want. And with a little bit of math, you can figure out how long that you need for it. Now, there is another type of ramp, which you may have seen before, and these are circular ramps, these kind of curved ramps. This is something that we can do as well. We don't see them being super common, but they can look really nice. They can also allow for some pretty efficient flow and pretty efficient travel. So here's an image here. You can see a car would be coming down this, and it kind of loops back in and around itself as you go from floor to floor. So we can do these. It will add square footage, of course, but they can definitely look nice and add intuitive user flow for the building. So we've talked about ramps. Now let's actually talk about the different kinds of layouts that we can have with a parking structure. And these are meant to be very efficient layouts. So of course we can have all kinds of quirky shapes, unique shapes, but if you're designing a parking structure, you want to consider these main types of layouts, because this is going to decrease that number, that square footage per parking space. So the first one is what I'll call a single bay with a dedicated ramp. So this is one bay. You can see here, this is parking space, drive aisle parking space. And that's it. It's going to be, like I said, roughly 18 meters long or wide. And then the length of it will just be however long you want that building. Now, because it's only a single bay, we can't use any of those kind of sloping bays. So we're going to have that dedicated ramp off of the side, and you're just going to use that as your way of getting up to all of the future levels, all of the higher levels in that structure. The other type of a layout would be two bays, roughly flat floors, but then you have a dedicated ramp off the side. So this is something you might see if you already have a parking lot. Let's say it's a fairly new parking lot, and you don't want to kind of dig up the whole ground floor. You don't want that kind of sloping floor system. You can just build on top. You still have to put foundations in. Foundations are definitely necessary for parking structures, but you can do two bays side by side. We would probably slope them inwards, so we would actually slope them down this way just by like 2% or so, and then we would put drains basically kind of along this middle grid line. But with this flat, relatively flat floors, and you just use this dedicated ramp to go up each level up and down. Then we come to this one, which I've talked about already, but we have a two bay sloping floor. So we can park on a maximum of 5%. You could do one side at a full 5%, or you could do two sides at 2.5% each, and you can get yourself up the parking structure just by driving around that helical flow. This is the image that I showed you before, and this is kind of what it could or would look like from a cross section. Then there's also the three bay sloped structure. So this is three bays with that middle bay being sloped. So very similar to how the two bay sloping floor system works. but basically you have 3 bays side by side, and you can use that middle bay at a slope of about 5%. You could also use these, I'll call them top and bottom bays here, to also slope up. So you could say do 2.5% and then another 2.5%, or you could do 4% and 1%, or any combination. Or you can do you could do 5%, 5%, whatever works to get yourself up those floors. And you can see just how this layout works. You come up and then you can go around and you can go around to get up and down the building. So here are some examples. You can see that this middle bay clearly kind of slopes down. And so that creates your ability to go up and down the structure. Same for this building here. So then this is that split level option I was talking about when I was talking about the ramps. So a 2-bay split level, you have 2 bays side by side. And then as you drive across from bay to bay, this is actually a ramp. So this ramp would be 12, 13%, something like that. But we have the length of 2 parking spaces back to back, which is going to be about 12 meters. We can use that 12 meters to ramp up half a level to get to the bay beside it. So if you're at level 1 here and you drive up this ramp, now you're at level 1.5. So again, here, if you're at ground, you go up half a level, and then you go up half a level, half a level, half a level as you go up. So again, very good usage of the overall square footage of your building. Here's just another example of what you can do with the split level. So you can actually add multiple ramps kind of in that same floor plate. So again, this is 2 bays side by side. You can imagine a line down here splitting the bays. But what this does is it adds extra speed to how you can basically empty the structure or fill up the structure, because you can kind of come up one and then down the other, and it just adds some extra speed to how you fill and empty the structure. Now, other layouts exist, and what I wanted to show here is to really talk about how this structure utilizes the topography of the site quite nicely. So over here, you can see it here, this area is actually quite a bit higher than kind of these parking lots down here. So if you already have topography in the site, use that to your advantage and build the structure so that you can actually access some of the higher levels just by using the topography of the site. So if you're building up like against a hillside or something like that, it's just very beneficial to use that to already get into those levels. So you can see here down below, we're entering, actually we end up entering this level here, kind of level 2, over on this side of the building. You don't see it, but we actually have an entrance down to the ground level. And then over here, we just have to ramp just a little bit up to get to that top level. So if you have that ability, by far, definitely something you want to consider, using the topography of your site to, just be as beneficial to the overall construction as you can. So in summary, we want to define basically the parking bay first. This is the first critical step. Then we want to plan out the width of the structure to be in increments of that parking bay, whether it's 1, 2, 3. I mean, we can go 4 and 5. We can go really as big as we need. There are a few limitations on overall area that you want for a parking structure, but by using that bay width, we can get to very effective layouts. Then the length of the building really becomes, as many grid lines as you need, which are just increments of the width of a parking space. And from that, we can get all of these different efficient type of layouts for a parking structure and a parking structure system. Okay, so now let's talk a little bit about roofs. So adding a roof to a parking structure is optional. And I first just want to make a note really about the wording that we typically use around roofs. So on the left here, we have 2 parking structures that we would say are open top level structures. We would say these do not have a roof. They simply just have an open top level. Compared to these 2 images, these ones here on the right, these do have an actual roof over top of that top level. I make this note because I see people sometimes refer to the top level as a roof regardless. And then they think that the roof is another level where they could park cars. But that's not how we refer to things. So an open top level, sorry, is a parking structure without a roof system, whereas a parking structure with a roof would have a roof system over top of that parking level. And so when we build a roof, we would typically use just steel decking on top of purlins and open web steel joists. We could simply use the same steel beam approach that we're using for the other levels, but the roof loads are typically much lighter, and so it's more cost effective to just use the joists compared to the steel beams. The roof itself, it can be a simple steel deck, or we could do decking with roof membranes if required. A roof is optional, but it is a good idea to keep the weather off of that top parking level. In a few slides, I'm going to talk a little bit about how we deal with snow. However, if you have a roof, you don't really have to worry too much about snow. So it can be a good option depending on the use case of the building. Now, parking structures are a great opportunity to add a pretty large solar array. So, with normal buildings, like typical office buildings, you'll have a bunch of things on top of your roof, mechanical equipment, vents, all that kind of stuff. And all of that causes shadows which would make a roof array, less effective. But parking structures, they don't have all those things on the roof. So, it's a great opportunity to add a nice large solar array. And Kiwi Newton, we have our own solar division, so we integrate these quite nicely into parking structures. And a parking structure itself does not take much power at all. So these arrays can basically, become a generating station for other buildings and basically act as some sort of generating hub, and you can get your entire property, towards a net zero type of a level. Because also as we look at how things are going, we see the number of electric vehicles on the road is constantly rising. So to service the increasing demand of EVs, parking structures can essentially become like mobility hubs and refueling stations. So electric vehicle charging paired with renewable sources of energy, such as solar panels, make parking structures a really important asset for things like campuses, hospitals, transportation hubs. And we see that's how people are starting to think of these kind of infrastructure projects. Okay, now parking structures, we need to make sure that cars do not fall off the edge. And therefore, we do require some sort of bumper guard, bumper mesh system. We achieve this with our bumper mesh system. It's galvanized steel, and it's a nice, light, and airy bumper system that is designed for the necessary loading to stop a car. So the loads that a bumper system has to take, those are clearly defined, and this bumper mesh system is designed to take those. So it's bolted onto the columns, as you can kind of see here. And we like it because it's not a kind of monolithic concrete beam that spans across. And I think it makes the entire structure feel a lot more open and a lot more natural light coming through the building. Now, of course, you don't have to leave the structure with just the columns and the bumper mesh. Now, you can if you want to. For example, this image here, this is pretty much the base version of a parking structure. It's completely code compliant. It will function perfectly as a parking structure. And this is really, this is kind of the best place to start when thinking about a parking structure. Start with the basics, start with the base design, and start adding from there. So this is the core part of the project that you really want to make sure you get right. This is the part of the project that really needs that sort of infrastructure thinking. But then what's nice is you can dress this up really as much or as little as you want. In fact, when I do budget estimates for people, I usually start with the cost of the base structure, something like this, and then I'll give them a few options for facade, kind of like a good, better, best kind of approach. And parking structures really are function first, but that doesn't mean you can't have a nice aesthetic and unique form. So you don't want to necessarily let the form trump function. You don't want things like aesthetics to really trump things like intuitive layout, longevity, or durability. But if you start with kind of the base, the core items, and then you think about the facade and all of the sort of add-ons, you can get the best of both worlds. And we have a really nice parking structure facade gallery on our website. And you can get some ideas and some inspiration of things you can do to make parking structures look really good. So you can scan this QR code, you can go to this website, and it's just a bunch of images of different parking structures and different facades. Let's talk about drainage. So I've mentioned it a little bit here and there, but there's kind of two main ways of doing drainage in a parking structure. We've got these, which I would call point drains, and then we have these, which are trench drains. They're kind of longitudinal trench drains. With this option here, if we have kind of one of those sloping systems where one of the bays is sloped in its entirety, we would put this nice trench drain right at the bottom of that slope. This trench drain it's actually just two C channels welded back to back with a flat bar in the middle. And again, that's completely hot dip galvanized. And then we put this grating on top and we connect it to the overall drain system. So this is a great way. All the water kind of slopes down from here and goes into these trench drains. If we're doing either a more of a flat type of a parking layout or a split level, we're going to tilt the parking bays, the flat areas of parking bays, more towards the center grid line. And then along that center grid line, we're going to have some of these point drains. So the water is going to come in, it's going to find these point drains, and it's all going to drain out. What's nice is with the point drains, I mean, with these trench drains as well, but with us, we don't do any core drilling on site to create these holes. We actually put this into the mold prior to the concrete so that our drain is there, and then the concrete and the rebar all go around it. The issue with core drilling, anytime you have to drill a core on site, you might hit some rebar and you might expose that rebar. So you've taken the cover off and that rebar is now, technically exposed, and you could get some water and salt in there, get into the rebar, and you'd cause a whole bunch of issues. Another thing that I'll say about drainage and plumbing for parking structures is we can actually drain the entire structure down into the storm drain. It doesn't necessarily have to go into the sanitary drain. We've worked a lot with the building code and different municipalities to make our case that all of the water, everything that comes in through the drainage, that can go right into the storm drain. This is, it might seem a little bit trivial, but if you don't have to get a sanitary line to this structure, it's a big cost savings. So let's talk a little bit about snow. So if you have a roof on a parking structure, you really don't have to worry too much about snow. However, if you have one of the open top level parking decks, then we do want to think about snow management throughout the design process. With our structures and our projects, we give the owners a full manual for winter management when we hand over the building. In it, we discuss things like salting, as well as suggesting a snowplow with a rubber-tipped blade. So a typical pickup truck can fit into these structures, and so a pickup truck with a snowplow with a rubber-tipped blade that can get to your top surface. And so two kind of, I guess, main options for how we're going to kind of control and deal with the snow on the top is one is to define snow drop areas. And in these areas, we would install basically like a gate in the facade, only on the top level. And the plow can basically push the snow off of the side of the building. So you can kind of see it in this image here, and you can see it a little bit better here too. Typically, what we'll do is we'll put a full wall, in this case it's a precast wall, all the way down the side of the building. And at the top here, you can't really see it, but the snow plow could be at the top and it could push all the snow. They would open this up and they just drop it. And then this area down here becomes a dedicated area for snow drop. It's got one on this side here as well. So you can see that here. So This is just, it's a great way. You bring up a truck with a snowplow and you push it off the side. You've got a wall down there. That wall basically just prevents that snow from kind of getting blown back into the parking structure as it's falling below. So we can also install snow chutes down the side of the building. Basically, these just help keep the snow in the snow drop areas and going down to where it needs to go. So in this one here, the snow plow could just basically plow it off. It goes into this snow chute that drops it all the way down to that dedicated snow drop area down there. And then I guess the other option, so the first option is basically getting a plow up there and pushing it off the edge, and you have dedicated snowdrop areas, and we've designed the structure in a way with either the walls or the snow chute. But the other option is just to have that plow come up to the top level, and we design an area on the top deck where the plow could push all of that snow. So for example, I don't know, let's say in the winter, we just define this area back here as an area where snow can pile up, and that plow would just push all the snow, and they keep it there. Um, so with this type of a snow management strategy, we would want to know that ahead of time because we would want to look at the structural system in that area. We just want to make sure that the layout is still going to work when you have piles of snow. And we might just design that area for a little bit heavier loading, knowing that it's going to be a snow pile area. And then also what I'll mention is if you have a dedicated ramp, so you have a full dedicated ramp, maybe it's 15% grade. That one's a bit more steep. So we can also look at putting electric heating elements into the UHPC slabs that basically create a heated ramp. It does add cost, of course, but it can also save on operational costs, such as your cost of your salt and your sand and your plowing. So something to consider and think about if you have a dedicated ramp. Lighting and signage. So something that I like about having the steel beams is that we also have this area between the beams under the slab where we can fit our lights and our signage. So this stuff, it doesn't have to sit further below the bottom of that steel flange. It can kind of sit in between those two. So we don't have to raise the floor to floor or the clear height distance for anything that drops, below that. So you can see here, we have the signage actually sitting kind of in the beam, and you can see it go all the way along. Same with the lights. Here we've got different signage up in the beams. So it's just a nice place to put some of that signage there. The structure itself is actually quite open. So a light structural system also allows a lot of natural light into the building. You can see in this image here, the lights aren't even on. So this is just natural light coming in the building, which, this is great for energy efficiency. It's also great for a sense of things like safety for the users inside the building. Just another point about signage, we can implement different kinds of parking signage out front and, other signage on the building as well, just as a nice aesthetic piece. And while we're talking about all of that openness and that natural light, it's also a great segue into talking about CPTED. So CPTED stands for Crime Prevention Through Environmental Design. And it is a major strength, really, of the Kiwi CarPark system. So the idea is it's pretty simple. Basically, design the structure so users can easily see, understand, and move through it safely. The Kiwi CarPark naturally supports this through the long span bays, the open visibility, bright LED lighting, and clear circulation routes. So instead of dark, confusing, closed-in parking structures, the goal of CPTED is to create an environment that feels open, intuitive, and actively monitored. So, for example, you can see in this video just how open these parking bays are. So this is the open span design. It allows, you can see from one side of the structure to the other because there are no big bulky columns really in this drive area. This is an entire parking bay that we're looking at. So what I like about this is you can put a security camera basically in this position, looking down the bay. So you put it at one end of the bay, looking all the way down, and you have really great coverage of everything going on. Another benefit of not having those big columns is there aren't any places to hide behind. So there's a lot of visibility between pedestrians and drivers. So if I'm a driver basically driving down this, if there are big columns in the way, there could be a pedestrian behind. I might not see them. They might not see me. But by removing those big columns in the drive area, everything is a lot more clear. It's a lot more safe for everybody walking through the building. And in addition, actually, in this video, let me restart it here. What I want to point out here, this was a good example. You'll note here, so we have a light here, and we have a light here. You can see this light is on, this light isn't. Because we have that natural light coming in, this light is actually, it senses the natural light and decides whether to turn on or off. So this is, again, great energy saving, but it's also just a really good use case to see, all right, we have all this natural light coming in, which natural light is really the preference, right? Natural light feels a lot better than artificial light. But since this is a little bit closer in, we can put the lights on over here, and we don't have to turn on the lights near all of that natural light. So you can just see, I mean, you just get a sense from this video how open these structures really feel. And one of the strongest Facades features that I really like about the Kiwi CarPark is that stair tower design. I mentioned it a little bit earlier, but in many parking structures, stairwells feel isolated, dark, and uncomfortable, but our approach is quite different. So typically the two inner walls, those are going to be your precast concrete walls, while the two outer walls use the ventilated glass. That means that people inside the stair can see out, but even more importantly, people outside of the stair tower can see in. And especially at night when that stair tower is illuminated, you can see everything that's going on in these stair towers. And then the ventilated glass, so there's actually gaps between the glass and the structure itself. So that's great because any noise, anything that's going on inside of that stairwell is also going to make its way outside. And just altogether, this makes users feel much, much more comfortable, and it discourages really any sort of unwanted behavior in those stair towers. And I sort of mentioned this already, but that open span design, it's exceptionally strong for setting up security camera coverage. Because there's no big columns interrupting views through the different drive aisles, the parking bays remain very visually open. That means that cameras can be positioned at the ends of the bays and capture, almost everything that's happening within that bay with very limited blind spots. So, the major advantage here is without any of those big columns, we can see end to end with our security cameras, and we can put them in really good spots. All right, so here's an interesting example to show operation costs between a Kiwi CarPark structure and then some of the other precast or cast-in-place options. So this comparison, we're assuming a 1,000 stall parking structure, and we're annualizing cost. So some costs don't happen every year, but basically if we were to look at, let's say, 10-year, 20-year lifespan, divide all the costs by the 20 years, this is roughly what an annualized cost is going to look like. So if we look at kind of some of these main items here, it is quite variable depending on how you design your structure, if you have a roof, if you don't, all that kind of stuff. But I want to just give a general idea to everybody that's watching. So, most of this stuff between the two options, it's generic. Life safety, elevator maintenance, of course, depends on whether you have an elevator or not. Electrical and lighting, doesn't really matter what kind of a structural system you use. Security, parking equipment, that's all going to depend on what you've got there. But where the kicker really comes in is structural maintenance and epoxy topping. So at the beginning of the presentation, or at least this part of the presentation, I had mentioned if we think about parking structures as infrastructure, we design them specifically for the usage that they endure, we can save roughly 90% on operations cost. And that comes down to this line item right here. We can go from about $35,000 to $350,000 just by the construction method that we use. The biggest reason here is that epoxy retopping. With the Kiwi CarPark system, we do not have nearly the structural maintenance in the epoxy that we have to do with these other systems. Because precast, cast in place, they need that membrane across 100% of the surface. We only need it in like 7%, which is just where two of our panels come together. So this is really the massive savings between the two. So you can see just what this does on a annual operation maintenance cost, significantly less by using this system. So there is a company in Europe called Goldbeck that utilizes a very similar construction method. It's essentially identical. And they have a study on CO2 reduction compared to traditional construction. So when comparing the full life of the building, manufacturing, construction, deconstruction, and recycling, so end of life kind of stuff, the Kiwi CarPark that system produces 20% less CO2 compared to conventional construction methods. Now, if we are only comparing the construction and the manufacturing, so we don't look at end of life, just construction manufacturing, the Kiwi CarPark system produces 32% less CO2 compared to other construction methods. So if we want to reduce the CO2 impact of building a parking structure, we should definitely be looking at construction methods like this. I have mentioned a lot of things in this webinar so far, but there are still a whole bunch of other things that haven't really gotten much of my time. So I'm going to go through this list incredibly quickly just to mention them and kind of touch on some of the key things that I typically get asked. So the first thing, can we integrate with different pay systems? Yes, of course. We build a really good durable structure. We can add any of the extras on top of that. So that's pay systems, that's parking gates and parking arms. We've worked with a bunch of different suppliers of those. We can bring that into our contract and make sure that it works effectively with the layouts that we're working with. Bicycle parking. So a lot of times we want to park some bicycles in here as well. Yes, absolutely. We can make this work. Those corner areas, those are great spots that I mentioned before for bicycle parking. If we need more, we can just allocate different areas for bicycle parking. Security integration. So sometimes we're building this on, let's say, like a university campus. They already have security with another supplier, or they have their own security. Can we integrate with their cameras, with all of their data? Yes, absolutely. We just need to know who it is, and we play nicely with that. Can we add panic station, those code blue stations? Yes, absolutely. Again, we've done it before. Very easy to add in. Can we work with different valet systems? Yeah, of course. I don't see any reasons why we can't work with any of those. We have seen some new automated valet systems, and we haven't had any in our structures, but I don't see any reason why we can't work with those as well. Wi-Fi access points. So, sometimes we want to make sure that we have consistent Wi-Fi throughout the building. We've worked with these before. We have them installed in some of our structures, so we can add that into our scope and make sure that we have Wi-Fi throughout the entire building. Elevators. So elevators are not required by code for parking structure buildings, but a lot of times owners do want them. So we can make sure that we design a structure with elevators, with the lobbies. The example that I gave in this webinar, that had elevators, so there's no issues there. Electrical, mechanical, IT rooms. Yep, we integrate those into our structures as well. We'll find a good spot for all of that kind of stuff and add it into the building. Parking offices or security offices. Yes, we can make sure we have some spaces throughout the building that can house all of that kind of stuff. If you need any additional conditioned areas, heating and cooled areas, we can make that work as well. We effectively find the right spot for them in the layout and whatever works for the programming, and we can add in some conditioned spaces. Parking operator preferences. So, again, this might be a structure for a hospital or a university or an airport. You already have some sort of parking operator, operating on your surface lots. We can make sure that we treat them as a stakeholder in the project. We can bring them into some of the discussions. We can use their preference for pay systems, barrier arms, all that kind of stuff. We can definitely work with whatever parking operator you already have. Secure access systems. If let's say this is employee parking, you only want employees, we can put fob systems on the stairwell doors, things like that. Parking doors, so the actual large commercial doors for parking. Yep, we can do that as secure access to a garage. If we want a big rolling door, we can do that. We can use high-speed doors as well. So if you want security, but you also want to limit the time that people have to wait for the door, we can do a high-speed rolling door to get cars in and out. Electric vehicle charging, absolutely. We've been seeing a lot of this lately too. We can put EV chargers into the project. We can find a good spot for them. We can make sure that the electrical service is sized for whatever EV amount is required. And design for expandability. This is a good one. I get asked this a lot, and it's something to definitely think about. So with our system, we can design a project to be expanded in the future. We typically want to know from the beginning, but for example, let's say you want to build a parking structure. We could design that structure for, I don't know, 8 levels, but maybe initially you only want to build 4. We can do that. And so we could build a 4-level structure, but the footings, the foundations, all of the structural, the columns and stuff, we would design all of that so that in the future you could add another 4 and you could get all the way to 8 levels. Definitely a good future proofing thing that you can do. The other option you have for expandability is to expand the footprint. So instead of going up more levels, you actually expand the footprint so you have a longer structure, or maybe you add another bay and you increase the width of your structure. The benefit of doing that, so the benefit of expanding in your footprint compared to expanding vertically, is you don't have to think as much about all of that future proofing when you're building the initial structure. So to build out horizontally, we would just add in new foundations, we would add in all new structure. Compared to if you want to do more levels, we have to think about, all that foundation stuff. The other thing is, if we come in and do more levels in the future, we really have to think about crane access. We have to reach further with the crane. Whereas if we're just doing an expansion of the footprint, we can use that same construction erection sequence that I was talking about before, where the crane basically erects a couple grid lines, moves back, does more grid lines. But yeah, future proofing and thinking about the future and how a system or parking layout could essentially be expanded. Great things to think about up front. The more you do up front, the better. And then extra features. So, sometimes building owners want extra lighting, above the building code lighting levels. We can absolutely do that. We figure out what sort of lumens you're looking for, and we just design the lighting layout to make sure we're getting all of that. Okay, so if parking structures are infrastructure, which I hope I've convinced you of that so far, then they need to be delivered with an infrastructure mindset. And so for infrastructure projects, the best outcomes happen when planning, design, constructability, prefabrication, and long-term maintenance thinking are all aligned from the very beginning. With the Kiwi CarPark system, those decisions are tightly connected. The structural system, the prefabricated components, the erection sequence, the layout efficiency, the life cycle maintenance strategy, they all influence one another. That is why a design build or progressive design build approach is such a strong fit. It gives the owner an integrated team early, and it improves transparency around cost and schedule and the different trade-offs that might come with the project. It also allows decisions to be evaluated more in real time, and instead of being kind of pushed downstream. So you want to deal with all of that stuff as it comes up, and you have the team that can basically figure all that stuff out as you're going. It also creates clear accountability, which that's just great for everybody involved. So design decisions really need to know the construction method in order to be effective design decisions. That's why you need everybody at the table from the very beginning. Now, can a parking structure that's already be designed end up being built with a Kiwi car park system? Yeah, potentially, but also maybe not. In some cases, we can adapt an existing design, but in other cases, maybe the layout, the spans, the ramping, different structural assumptions might not align well with the system, and so we'd have to redesign it. We can save all that redesign if we're involved early. The Kiwi Car Park System, it really is more than just a collection of columns and beams and floor slabs. It is a full methodology. And that methodology works best when the team responsible for the planning, the design, the fabrication, the construction is working together from the start. Owners who engage us early don't just benefit from using a modular construction system, they benefit from the Kiwi approach. Because a true modular system is not just the modular components. It requires a project delivery methodology that leverages standardization in planning, design, manufacturing, and construction. The Kiwi approach brings everyone to the table, including the owner and their stakeholders, to make sure that the decisions being made are optimal for the project. So with this approach, you benefit from a pre-assembled team that knows each other's efficiencies, all managed by Kiwi Newton. The whole team has completed many parking structure projects together before, and we bring that experience to your project. Compared to a design bid build project delivery, the Kiwi approach is significantly faster, results in better decision making, and reduces finger pointing and reduces cost overruns. This approach closely resembles a design build project model with the benefits of using a team who's already worked together and knows how to work efficiently. So if you're interested in working with Kiwi and you have a parking structure project that you're interested in having us take a look at, the typical steps kind of follow this sort of a framework. So first, we have the initial inquiry and kind of high level budget. So with the initial inquiry, we can consider your concept and start with a high level budget price. It's best to get a sense of the project costs early to see if we're even in the same ballpark. We don't want to do too much work if we're speaking different languages in terms of cost. Now, although these budgets they don't include detailed line items, they're typically within 5 to 10% of the actual cost, just with a high level budget. And we can do that because we've built so many of these, we know the costs and we know how things are going to go. So we can give a pretty accurate, just high level concept price. Stage 2 is a preliminary design contract. So typically projects are going to have some sort of pre-consultation meeting with the city. And so it's helpful to have preliminary design drawings with some basic massing, project stats, GFA, parking spaces, all that kind of stuff. So we can develop this design package for a small fee. It depends on the project size. From that new layout and from some, development of that design, we can perform a more substantive estimate, more of a Class B type of an estimate, and develop a full scope, including allowances for like site works, servicing, all of that kind of stuff. Also at this stage, we might suggest obtaining some of the necessary like reports and surveys, like geotech reports, soil reports, environmental site survey, all that kind of stuff. We can also manage this process and just help you get all of those reports that you're going to need for the project anyway. The next step would be around the site plan application. So we will work with you and any of the other required consultants, whether it's civil, landscaping, specialty consultants, to handle that site plan application process. That SPA management contract will be with us, and then we will end up hiring all the other consultants with your approval, of course, to manage that site plan process. And once that process is complete and site plan is essentially approved, we'll move into a CCDC 14, which is a design build stipulated price contract. So once we have that scope, We'll do a more definitive estimate, gets us to a Class A. We'll get a full scope of work proposal, which will be used as a contract document in that CCDC 14. We'll assemble the full project team, develop permit-ready drawings, and really manage that entire building permit process. Then we move into fabrication, mobilization, and construction. Once we've got that permit, we initiate basically that construction phase, and you start seeing the project take shape. And then number 6 is occupancy and commissioning. The final step involves commissioning the building and handing it over to you. And then 7, it's an optional item here, but we can have a maintenance contract where we basically take on the maintenance of the structure. We are very committed to our work, and so we offer those maintenance services for all of our buildings. We also have warranty packages that extend beyond just a standard warranty. I think we've done 10-year. We may have even have done a 20-year warranty. I know we've offered 20. I think we've even offered up to a 30-year warranty before. I don't know of any other construction company that is offering those kinds of warranties. But again, we know the system. We know what we're working with. We know the quality of the construction we do. So we are able and interested to do those kind of long-term warranty contracts. Okay, and I believe that is where we're going to leave it. Now, just before I get to the questions, one of the last things I just want to mention here is, look, we've gone through a lot of things today. And there's things that I still haven't really been able to include. So I just want to direct you to our website. If you go to About and you go to Articles, you're going to get to this page and you can filter by parking. We have a ton of really good articles here. This is a great resource. If you have any questions about parking structures, I would suggest just flipping through this. A lot of good articles, a lot of good information on here as well. Okay, so with that, I think, let's see, I think Janine has been compiling a few questions here. So let me see if I can pull those up. Yes. All right, so these are some of the questions that you have been putting into the Q&A just throughout the webinar here. Let's see if I can get to these. We have a couple more minutes left here. I know this has been a really long webinar. I just wanted to have one full encompassing webinar about our Kiwi CarPark system. So first question, what are the dimensions of the steel columns? Good question. So the length of the column, I mean, that's just going to be whatever makes sense for the height of the building. And we might break it up. So if we have a really tall structure, we might break it up into two different columns. But the important dimension from sort of a planning perspective is really more around the profile size. So if we just go, let's go back to here, for example. So usually this is going to be about a W300, maybe a W250 or a W300 section. So typically what I do is if I'm doing some sort of high level concept planning, I leave about 300 millimeters for basically the depth of this column. So I'll leave about 300 millimeters here and then 300 on the side and 300 on the other side as well. Like I said, it's usually anywhere from 200 millimeters to 300. So, for a planning perspective, using that 300 dimensions pretty good. And then same with the width of the flange is usually around 300, 200 to 300, somewhere in there. How are the steel beams connected to steel columns? So we use bolted connections. It's two angles with bolts through the beam and then bolts into the column. All of that, again, is hot dip galvanized. Can we do 1.5 bays wide? Yes, you can. Well, kind of. If we go back to, let me just pull up a slide. Let's take a look at this one, for example. So, yeah, this is 2 bays side by side, right? If you had 2.5 bays, you're basically splitting the 1 bay kind of down the drive aisle. Probably not ideal because you can't really do much in that space. But what you could do is a bay, and then instead of half a bay, it's more like 2/3 of a bay, where you have at least one parking space and the drive aisle, and then your dimension of your building would just be, one bay plus the parking length plus the parking aisle width. You can do it. What it means is you only have a single loaded drive aisle here. So instead of parking on both sides, you can only park on the one side. It's doable. It can be done. The efficiency of your layout in terms of square footage per parking space is just going to go up. So, if you're completely locked in and you can't fit a full 2 bay side by side, but you could do a bay and a little bit, something to consider, although it might make sense to just maybe add a couple more extra levels and just do a single bay with a dedicated ramp off the side. Let's go back here. Can the system be used for underground? Yeah, so underground parking is quite a bit different than above grade structures. However, we can use this system for underground parking. The differences are the fire rating requirements are quite a bit different when you go underground because now it's considered an enclosed building. So the steel columns and the steel beams, we're going to have to spray on some fire rating on that. Or we can do intumescent paint, actually. We'd probably do that instead. And then the parking deck itself. So instead of using that 105 millimeters, we would go to the 125 or 130 millimeters. We just thicken that up because it's a fire rating thing. So we can use it for underground. Underground also tends to get a little bit more tricky because you usually have some sort of structure on top, whether it's a building or, I don't know, a park or something. Um, it changes the structural system a little bit, but it still is fairly cost effective to use this kind of a system underground as well. What about car elevators instead of ramps? Yeah, we've looked at these a couple times where we were looking at garages where space was it was really tight on space. Car elevators just end up being quite expensive. We've never actually ended up putting them in, but I think I've estimated them several times. They've never gone through. They tend up being really expensive, and then you also have to consider the maintenance of any sort of mechanical system like that. Like if you're a public garage, for example, or maybe you're building a parking garage for a residential building, if you have to sit there and wait for an elevator, like a car elevator, and someone else is trying to get out of the garage, and then that car elevator breaks down. It's just a big maintenance headache. So people think about them, but I don't know if they're really as ideal as maybe others as you might think of at the beginning. Does Kiwi do the facade as well? Yeah. So typically, all of the facades we've designed them. I mean, we've had architects work with us specifically where they just took over the facade piece, but we fabricate the facade. We've got our own facility for all of our steel fabrication, aluminum fabrication. We do powder coated steel profiles quite a bit, so we can do all of that. We put that into the contract. And yeah, then it's just better to have kind of one contractor on the job. How does this stand up to earthquakes? Yeah, lateral loads is actually that's a common question. I'm surprised I didn't put this one in already. So it holds up actually quite well to earthquakes. And the nice thing is our structural system or our entire parking structure is very light. So if you know about earthquake loads, earthquakes, the size of the load is a function of the weight of your building. And so the more weight you have in a building, the higher your lateral loads are actually going to end up being. So for earthquakes, the lighter your structure, the better. And so that works really well for us because we have very light system, right? Light steel columns, light steel beams, and then this very kind of thin precast concrete deck that sits on top. And then in terms of lateral loads, so we can fit in these bracing systems, wherever we need to. So we actually have a lot of opportunities to add in lateral force resisting systems. We can do it with bracing. We've done it with stair towers before. We do have to be a little bit careful with stair towers just because we don't want to lock in the building between kind of two stiff stair towers because we also have to worry about thermal loads, expansion and things like that. So a lot of times what we do is actually all the lateral loads are taken through a bracing system, whether it's on the edge of the building. Sometimes you can kind of see it here. This is a middle grid line, so we put it in there as well. But yeah, lateral loads for earthquakes, very good because we're a very light building. And actually, that the weight of the building is also very beneficial for foundations. So if you have a site with very poor soil conditions, we can still get one of these structures on the site because it's such a light building. We don't need nearly as large of a foundation to sit on that poor soil. And we've had projects in the past that have come to us because other ways of building a parking structure weren't going to work with the soil that they had, and we were able to get our foundations in with our later structural system and ended up with a really good parking structure system. So yeah, lateral loads typically aren't an issue. What are the little squares on the parking deck? Yeah, that's a good question. So if we go back to, let me pull this up here. Right here. This is a good image here. So you can see this is actually the top surface of our parking decks. So obviously this is a parking deck that's rotated 90 degrees, but this is the top surface. You know, you can kind of see this like tactile surface on the top here, but this is what's going to be on the top surface. Why do we have these little squares? It's actually for traction. So concrete can actually get very, very smooth, especially if you have something wearing on it at a regular basis. So these little dimple pattern in the top of the deck, it actually allows for the cars to have better traction on the top surface of the garage. One kind of funny side benefit is when you have a structure with this dimple pattern across the entire surface, it's also a big deterrent for skateboarders. So you don't have skateboarders, you know, hanging out in your garage and, you know, doing all their skateboarding and their tricks in here because it's just not a nice, not a nice surface to skateboard on. So that's what this is all about. We actually pour these upside down. So you can kind of see it here, but this is one of the deck plates being fabricated. This is actually the bottom surface, and then the top surface. So it's actually top down, and then we flip them over. So this dimple pattern is actually in the mold on the bottom of the mold here. Can we build affordable housing on top? I get this question all the time, and I get variants of this question, which is, can we build a tennis court on top? Can we build a park on top? Can we build a restaurant on top? The answer I always tell people is with enough money and manpower, you can do anything you want. But there is a big trade-off anytime you want to build on top of a parking structure. And actually, I have a whole article that I wrote about this. Can you build on top of a parking structure? What did you need to know? If you're interested, I would highly suggest reading this. The long to short of it is, if you build something on top of a parking structure, you change the entire building's classification according to the building code. So a above grade parking structure is considered in the building code as an open air structure, or it's actually a storage structure. And because it's classified like that, we can get away with some really cost effective construction because the requirements change. We don't need big HVAC systems. The fire rating of the materials changes. Vibration and deflection limits, those change a little bit. So we're in this kind of sweet spot of the building code that allow us to build open air structures very, very, very effectively. The minute we put something on top of that, the entire building, or at least everything underneath that kind of top little piece that we're putting on, that entire building underneath now has to abide by the building code classification of what's ever on top of it. So by putting affordable housing, by putting a park, by putting a restaurant, you now have what the building code would consider an occupancy type sitting on top of your open air structure. So because of that, that occupancy type has a lot more requirements, right? You have occupancy up there. So fire rating is different, plumbing is different, um, sprinklers, fire alarms, big HVAC systems, all of that is different, and it puts it into a more of a enclosed building kind of type. And so your entire parking structure now has to be built according to that building code classification just because you've put something on top. So what we usually try to encourage owners, if they're trying to get some sort of kind of multi-use out of this building, is to really consider separating the building in the footprint. So remember when we were watching the erection sequence for Humber College, this one right here. So I had mentioned while we were watching it that we kept this little office building here, we kept this out of the footprint because this is a different type of building, a different building in terms of how the building code sees building. This would be occupancy. This is an office building, it's retail, there's a coffee shop. So this is an occupancy type of a building, and then this is open air structure over here. So what we did is we separated in the footprint. So the building code actually sees these as two different buildings. We have a nice firewall that separates the occupancy building from the parking structure building. And so now this can be built like occupancy. This can be built like parking structure or open air structure. And this is the best way to do it. So if you are looking for some sort of multiple use case, try to separate them in the footprint of the building and not put something on top. And just to give you a little bit of a way to qualify that, a parking structure, open air structure, you're maybe looking at, all in costs of, I'll say about $100 a square foot. That's a very cost-effective way of building open air structures. The minute you get into occupancy type buildings, you're almost right away at like $200 plus a square foot. So just by switching the classification in the building code, you're pretty much doubling the cost. So if we were to take this office and say, put it as the top level of this structure, all of the square footage of this now goes from $100 a square foot to $200 a square foot, plus the $200 a square foot for this office use on top. So yes, you can do it. You can build something on top with enough money and manpower. You can do anything. But the smart way to look at it is to say, okay, how do we actually separate this as a footprint and have one building, over here and the other building over there? And yeah, highly suggest you take a look at this article. It goes a lot deeper into, what you can and cannot build on top of a parking structure. This is an AI generated image, so please do not put a fair or a circus on top of a parking structure. That was just, that's this image. We just use a little AI to make it look better. Okay, so that's all of the questions. I have a feeling that everyone's just ready to be done with this webinar. This is by far the longest webinar I've ever done. My voice is getting a little bit hoarse. So I really thank you all for taking some time to sit here to watch the webinar and to be a part of this today. I will be sending out a recorded version of this. So, give it a couple days and you'll be getting a copy of this as a video. Feel free to go back and watch it, of course. And if you have any other questions, any other comments, you're thinking about a parking structure project, please feel free to reach out to us. And we'd be happy to take a look at your parking structure project. With that being said, thank you very much. And I hope you all enjoy the rest of your day.